So in the last few videos, we got an introduction to differential equations from, thinking about what they are, thinking about why we might be studying them, to thinking about, how we can analyze a potential solution for a first order differential equation just by essentially drawing some pictures to help us kind of get an idea of what the solution is doing without actually solving the differential equation. But now we're going to tackle, actually being able to solve at least one particular type of a differential equation. And so before we dive into that, I'm going to introduce us to two more classifications for differential equations. So the first one is, you might notice that there is an O in front of the differential equation part of this little abbreviation over here, and the O stands for ordinary. And so differential equations are classified as either ordinary differential equations, which essentially means that our differential equation has full derivatives in it. So, you're going to see things like dy dx or y double prime and things of that nature. And non-ordinary differential equations are referred to as partial differential equations. And partial differential equations involve something that if you haven't taken a multivariable calculus class yet, then you'll see very soon after this one, because this is a Calc 2 class, but you would see something like partials, dy, dx, things of this nature. But everything that we're doing in this class involves good old-fashioned, what we would call ordinary derivatives, and so we abbreviate differential equations as ODEs, because ordinary differential equations. The second classification is going to basically spearhead, what we're going to be doing in this video, which is that we need to define this word that is at the title, which is what is a separable differential equation. And a separable differential equation is a little bit kind of tricky to define, in my opinion, but maybe I can just do it. I'll try to shorthand it a little bit. The idea is that a differential equation is separable if we can get it in this particular form. And for now, we're going to stick with, ordinary differential equations, and we'll stick with the variables y and x, just not to make anything confusing. The idea is that, normally with a differential equation, we have a hodgepodge of stuff. There's an equal sign somewhere. We have some, stuff on the left side, some stuff on the right side, and there's derivatives and yada yada. So we're going to be dealing with first order differential equations, aka, a differential equation that only involves dy dx. And the idea is that it's going to be considered separable if I can write it in the form where if I put everything with y on one side, that I'd be able to write it like this. And if I put everything with x on the other side, I'd be able to write it in this particular form. And this is literally what it means if our differential equation is separable. And I think that it's pretty challenging to kind of, understand it very well just by looking at this. So let's see if we can get just a nice, easy example. So for instance, a first order differential equation that is very readily separable is the following differential equation: dy dx is equal to xy. And this is easily separable because what we can do is we're going to treat dy dx as a fraction, and we're going to put everything with x's on one side, just like you see here in the definition, and we're going to put everything with y's on the other side, and hopefully it fits into this form. And you'll notice that if we do that here, right, if I multiply both sides by dx, I get dy is equal to xy dx. And if I divide out the y on both sides, then I'm going to get 1 over y dy is equal to just x dx. And you'll notice where, in the last videos, we have done things like, you said we know how to analyze a first order differential equation like this by looking at slope fields and drawing pictures and trying to figure out what the solution is doing. Now we can actually go about solving this, because at this particular step, right, we need to remember that our goal is to solve for the variable y, right? We're solving for some function y equals blah stuff in terms of x, and we can actually go about solving this, because the next thing to do would be to simply, let's not do that. The next thing to do would be simply to take the integral of both sides, right? We can apply an integral to both sides, just like you could apply the square root to both sides if you really wanted to, or a derivative to both sides. We can take the integral of both sides, and hopefully we will get two things that we can very easily solve. But before I do that, I'm going to run through a few more examples of some separable differential equations, or maybe one that's not separable. So, for example, if you're given the differential equation x plus y prime is equal to 3, let's examine whether or not this thing is separable or not. So the first thing that I would do is I would put everything that doesn't have a derivative in it on one side. So I'm going to and rewrite y prime in terms of dy dx. So I'm going to have dy dx is equal to 3 minus x. And you'll notice that if I multiply both sides by dx, we get to the point we have dy is equal to, put it in parentheses, 3 minus x dx, and we're good to go, no problem. So it turns out this is a separable differential equation. Hip hip hooray. But what if I had modified this thing just a little bit, and instead of having a 3 here, what if I had a y here? What if I put a y on the right hand side there? What would change in this whole process? So instead of having 3 minus x, now I have y minus x. And you'll notice now that we run into a little bit of a problem, which is that if I multiply both sides by dx, I get dy is equal to y minus x dx, but there's no way for me to get this y on the left-hand side and to be attached to the dy, right? It's not possible. Some people, you might say, well, what if I had taken this y and subtracted it to the left-hand side first and then multiplied by dx? The math still works out the same way. So if I were to have done that, I would have gotten, dy dx minus y is equal to negative x. And again, we're still going to run into the problem where if I multiply both sides by dx, I'm going to end up with dy minus y dx is equal to negative x dx. And unfortunately, we can't do anything at this point because we can't integrate, everything perfectly. I could integrate the first term, I could integrate that third term, but this one is going to lead me to sadness. And so, in these sorts of examples, you just have to kind of be careful with how you move things around and trying some algebra and seeing what works and what doesn't. People kind of always ask the question, how do you know if you've done it right? Like, how do you know, what if you had thought that this was separable when it wasn't, or vice versa, right? Maybe we looked at this one and we thought it wasn't separable, but it is. And I'm going to say that the more examples you do, the more familiar you're going to get with it, and the easier it's going to be to tell, like, okay, yeah, I've tried enough algebra, and there's no way I can keep things apart, or it is possible, and I can get things into this form right over here. Maybe one more example. I think I'll throw in one that usually is tricky. Let's see here. What if I have something like y prime? Let's see, what could I have? Let's do xy prime plus x is equal to, let's see, what could we do here? Xy prime plus x is equal to, I don't know, let's do equal to 1. Okay, so is this separable or not? So if we try this one, right? If I have x, y prime is equal to 1 minus x. Now at this point, again, our goal is to separate the dy's and the x's, but I can divide both sides by x first, and I'll get y prime is equal to 1 minus x over x, and now I will be able to split this up, because I'll have dy is equal to 1 minus x over x dx. And so sometimes, problems that look like this, you can factor things out, you can move things around, you can divide things out, and sometimes you can't. So I don't want to spoil all the fun, and I'm simply going to say, maybe there's going to be a homework problem or two that, you're going to have to think a little bit outside the box as to whether or not it actually is separable or not. But, since we have kind of like the idea, right, the reason why this is in the Calculus 2 class is because, in solving these problems, we're going to need to do a little bit of Calculus 2, do a little bit of antiderivatives. And so let's take this one that we were working on here in the upper left-hand corner here, and let's actually work through this problem. So this was a separable differential equation. We got it into its separable form right here. And so now we can go about solving this particular problem. Because if I take the integral of both sides, right, very carefully, on the left-hand side, I'm going to get the natural log of the absolute value of y, technically plus c, and I'll address that in a moment, is equal to x squared over 2 plus c. Now, at first you might wonder, why didn't I write a plus c on the left side here? And the reason is because, when you do the antiderivative on the left, there's going to be like plus some, constant that comes out. And when I do the antiderivative of the thing on the right side, there's going to be plus some other constant that comes out. But I could take this first constant and I could subtract it to the other side, and you'd get, in this case, b minus a. And I'm just going to package that into some brand new constant and call it c all the same. And so in this particular case, we can be kind of lazy and just say, it's not that there is no plus c that shows up on the left-hand side, it's just that it's going to get absorbed by the plus c on the right-hand side, so we're just going to leave it as is. And now, we're practically finished with this problem. The final step would be, how do I get the y by itself, because the goal is to solve for y. And we need to remember that our exponentials and our log laws. And so it turns out that in order to do that, we're going to exponentiate both sides and raise both sides to a power of e like so. And we're going to remember that e to the natural log of something is just the thing on the inside. So that's going to leave us with the absolute value of y is equal to e raised to the x squared over 2 plus some constant c like so. Now there's a couple things to note here at this particular point. First off, technically we're practically done. But the first thing I want to point out is that the value of this particular function here, right? We have an exponential, e raised to some power, is never a negative number, right? This thing is always greater than 0 because it's exponential, right? There's no way to get any negative number. You can't even get 0 no matter what you put in the exponent there. And so the point of that is that, do I really need these absolute value bars? And the answer to that is no, so I don't need those. So that's actually a really nice thing we get to drop off. And the next thing that we get to notice is that we can use our exponent rules to rewrite the right-hand side in the following manner. We could write it as x squared over 2 like that, but then I can write times e raised to the power of c. And why am I doing that? Well, last time I checked, e raised to the power of c is just another brand new constant, right? This is just some other brand new constant. I'm going to call it bigger c. And so we get to our final answer finally, that our final solution, our final general solution anyways, is going to be c e raised to the x squared over 2. And we're going to be content with this as a solution. Now, if I zoom out just a smidgen, right, we want to remember that our original differential equation was this. And just for the sake of the fact that it's our first time learning it, let's check that this is indeed our solution. So in order to check it, we're going to need to investigate dy dx. And last time I checked, if we take the derivative of an exponential, it's just going to be c e to the x squared over 2, but then we're going to multiply by the derivative of x squared over 2, which I believe is 2x over 2, or just in this case going to be x. And so we're going to notice also that, this chunk here, the c e to the x squared over 2, lucky for us, that is our proposed solution for y. And so we do fit the solution that the derivative is equal to x multiplied by y, right? There's our x, there's our y, and so it checks out. That is our solution. Now, you may remember back to when we were talking about the slope fields, that if I were to plot out this first order differential equation onto a slope field, that there are going to be hundreds of solutions, not even hundreds, infinitely many solutions, right? Because we'll get a whole bunch of these dashed lines that go in a whole bunch of different directions, and our solution, does a bazillion different things kind of depending on where our initial condition was, right? Like if we were dropping a leaf in the river, depending on where we drop it, the leaf floats in a particular direction. And if you remember from those videos, I had said it's because when we solve this differential equation, we're going to have some constant c here that really affects what our solution looks like. And in order to be able to solve for that constant c, or for this scalar coefficient c, we would need to be given some initial condition. And so what I mean by that is we're going to throw in this thing, which is actually, I guess I can erase all of this. And let's just modify the start of the problem to just have been given a little bit more information. So if the start of this problem had said that, solve the differential equation dy dx is equal to x times y, but let's say, we were given some sort of initial condition, right? We knew that at the start, so let's say this is a differential equation that has to do with the weather, okay? Where y is the temperature, and x is like, I don't know what day it is. And let's say that just on day 0, right, when we started our experiment, we saw that the temperature was 70 degrees. Okay, so we're given this initial condition, and this is the equivalent of, on that slope field, knowing that at the point x is 0 and y is 70, it's knowing that our solution has to go through that point. It has to go through 0, 70. So even though there may be, all these other dashes that we get from plotting points on our slope field, we know that our solution is not going to be any of the ones that kind of go down here, or any of the ones that kind of go off in some sort of wonky direction. It has to be a solution that goes to the point 0, 70. And so now that we have that information, that is going to allow us to solve for this unknown scalar coefficient c fairly easily, because since we have that our solution is y is equal to c e to the x squared over 2, but we also have this condition that says, well, not only is this our solution, but we also know that when x is equal to 0, the y value must equal 70. We can plug in our initial condition, and that's going to give us that 70 is equal to c times e to the 0. And last time I checked, e to the 0 is just 1. So that's going to tell us in this particular example that the c value that we're missing is going to be 70, in a very similar way that we used to have to solve for the unknown coefficients, like when we did the velocity and acceleration problems, right? You had to be given, like, if you started with the acceleration and you wanted to get velocity, you had to be given an initial condition involving the velocity. If you wanted to go back to the position function, you had to be given an initial condition also involving the position, things like that. And so what this does is basically says that our final solution, our real solution that satisfies this initial condition as well, is actually y is equal to 70 e to the x squared over 2. And we're done. Life is good. And that's honestly pretty much it about separable differential equations. If you're able to put it in a separable form, like we were in this particular problem, right? We were able to put it in a separable form and slap some integrals in front of it. Then the only thing that limits us from being able to finish solving this differential equation completely is whether or not we can actually perform the integral that we've been given. And in this particular class, at this particular level, you're not going to be given any integrals to solve that you wouldn't be able to solve. Otherwise, it'd be a pretty boring lesson on how to deal with differential equations. So yeah, I'd say that's pretty much going to do it for this video, right? Separable differential equations are a fairly easy concept to understand. We have a goal, we have a target form that we want them to look like. Sometimes we can get them in that form, sometimes we can't get them in that form. And I'd say to look at the textbook, pop open a textbook, just to see a few more examples of ones that we can get in that form, maybe some that look like we can get it into the separable form and we end up not being able to do it. But like I said, once you attack some of the homework problems, they're going to feel a little bit easier and maybe make a little bit more sense, and then it's not going to be too intimidating. So yeah, that's it. That's the end of our Calculus 2 class, so to speak. This is the last video that covers material specifically from this class, so congratulations on making it this far. As always, if you have questions, ask away, post them in the comments or in the discussion, and then hopefully we'll continue on to the multivariable calculus course next.